Okay, so we're ready to go over numbers 4 and 5 of the assignment.
The size of cheesy bread.
Yeah, it's in the fridge. I told you not to bother me while I'm doing these things. But nothing. This is time sensitive. It's important.
You don't love me.
Annabelle, that's got nothing to do with it. Look, I'll see you in a little bit, okay? Just get your cheesy bread from the fridge, and I'll see you in a little bit, okay?
Okay, you got have fun with your chemistry. I'll eat my cheesy bread alone.
Look, I'm sorry. I know you're upset. I just
Just shut your box and eat a knob. Fucking wanker.
Jesus Christ. Sorry about that. She's kind of dramatic. So we're continuing with number 4. And as I say here, it takes 3 steps to do this. And graphically, I show going up, flat, and up again. So these are the 3 steps you want to look at. So you have heating the ice first. And so that is like when the ice is still ice, but it's just getting hotter. So it goes from this negative 10.5 degrees Celsius to 0 degrees Celsius, which is the freezing and melting point of water. So when you see the symbol, so I got to bring up drawing tools here. So the change in temperature, that is 10.5. If you had like something different, like another substance other than water, you would need to perform the subtraction. But from negative 10.5 to 0 is just 10.5. So this particular equation is not shown on the first sheet of the explanations, but this is about specific heat. So changing Q. So Q stands for heat. So you're looking for the change in heat, which is an energy amount, like how much the energy changes. And specific heat is usually dealt with with mass rather than moles. And then you have C. Now C is the specific heat. So whenever you see these values here, we're looking at that's C. So we start off by how much ice we have, which is this, and we multiply it by the specific heat of ice itself. So all 3 phases, you have solid, liquid, and gas, have different specific heats. So here we know this water is like one of the few things where we have like names for all these things. So this is ice, this is water itself, liquid water, and then we have water vapor. And we're not going to be dealing with all of those because we're going from ice to water. So the second step, first let me back up a little bit. I did the calculation here and then rounded it. I decided though maybe not round until the very end. So in the very end, I'm adding all these amounts and I'm adding everything with the decimal values and then rounding to get to the end. So it's like a little bit of change from the work I did there. Okay, so the second step is ice becoming water. Now in this step, the equation is a little different. You have the change in heat is the number of moles N times the change in heat fusion. So really this particular chart should have 5 numbers. It should have the specific heat for a solid, the change in heat from a solid to liquid, which is the heat of fusion, and then the liquid specific heat, and then the change in heat for vaporization, and then the gas. Now it only has 3, but I gathered numbers from the previous problem because it did tell me it looks like it was a little cut off there, but I did use this amount here. This was the heat of fusion, which is also the heat of melting for this step. Okay, so you notice how this equation and this other equation here look a little bit different. Okay, so we start with the amount of grams for water, or the ice in this case. And then we use this here. This is, I decided I wanted to use this amount, 18.02. That is the molar mass for water. And then times this heat of fusion or heat of melting, however you want to put that. Now, something to notice here. Here we have 797 joules to heat the ice to a certain temperature. And while it's becoming water, it's 12 kilojoules. That's 12,000 joules. So it's quite a bit more for something to change state. It takes a lot of energy to change state, which is why we have this flat line here. That flat line represents that the temperature is not changing, but energy is being added in order for it to eventually become a different state. So in this little simple diagram I have here, here's what everything represents. You have the ice heating up, ice is getting hotter, and eventually here is 0 degrees Celsius, which is the freezing point of water. So that's when ice becomes water or when water becomes ice. And then you have this point, which is the water getting hotter. So the last step is the water getting warmer. And we're back to this equation again. Okay, notice it's the same as this first equation, except that the C is going to be different. So I used the C here, which was the specific heat of a solid, the specific heat of ice. This is the specific heat of water. This is a rather high specific heat. It's because it actually takes a lot of energy to warm water. If you ever cook, you know this by it takes a long time to boil water. And I put this, now this is the change in temperature. So it's not just the 22.5, it's really 22.5 minus 0 because that is the freezing point of water. So from freezing to this temperature, you're looking at a change of 22.5 degrees Celsius. It gives you this amount, and I rounded it. But again, when I added everything, I chose not to round it there. So all these have all the decimals in there. You add them all up, and you get this amount. And then we got to work that out to make sure we have the correct sig figs. Now, the sig figs for this, want to base that upon the information given. So we have 36.0 grams. This also has 3 sig figs here, 22.5, negative 10.5. These have more, but you don't want to use that. You want to use the least amount for sig figs. So that's 3 sig figs. So that's why I put 162. This is in joules. Well, I think it looks a little bit neater when you put it in kilojoules. So this right here should be our final answer. Now, number 5. I don't know how to pronounce that. Naphthalene. It's a primary component of mothballs. Mothballs are these things that grandmas have. Or they put them in their drawers to do God knows what. I don't know. I think this is like moths eat your clothes. Like one time, actually, a moth did eat my clothes, and I didn't know it was a moth until somebody told me like that was the problem. But they're like nasty butterflies, like eat clothes. So this one says the heat of sublimation is this. So let's first wrap our heads around this word sublimation. What does that mean? So this is a bit hard to understand because we don't see this much in real life. We're pretty used to the way water works. Water is ice, and then it's water, and then we boil it, it becomes water vapor. Not everything works like that. Sometimes things go straight from a solid to a gas. The best example I could think of is dry ice. So dry ice is actually frozen, I believe, carbon dioxide. So I'll write that out so you know what I'm talking about here. Um, Back in the day, I used to go out to Penn State a lot, and we get ice cream, and we'd take it home with us, like a 4-hour ride with ice cream. And the way it would keep cold is they would pack dry ice in it. So dry ice was like these huge blocks of. They actually looked like regular ice, like water ice, but they weren't. It was frozen carbon dioxide, and it didn't melt. So the frozen carbon dioxide went straight from like a block of what looked like ice into a gas, so gaseous carbon dioxide. And the benefit of that is, first of all, dry ice is very, very cold. And when it turns into a gas, it doesn't melt, so you don't have everything getting all wet. So that's the purpose of that. Beyond that, you don't really need to know too much about this to answer the question. because it doesn't mention much about temperature except that it happens at room temperature. I don't know anything about mothballs or how they work and stuff, but it is this chemical. So we'll go straight to the equation. We have Q equals N and delta H. So Q stands for heat. Heat is basically energy. So we want to know like how much energy it takes to do this. I said here how much energy. No longer talking about dry ice, so let me scratch it out. N is number of moles, and delta H is a certain number that we're given by a chart or in the problem based upon what's happening. So here's the calculation. So we have the grams of this substance of C10H8. I like to put that in just to show my work throughout everything. I don't know if you're required to do that, but just be clear about all that. So here is the molar mass of C10H8. They give it to you. If they didn't give it to you, you'd look on the net, just type in molar mass C10H8 or whatever the hell this word is here. You can calculate it yourself. So carbon is about like 12 for molar mass. Hydrogen is about 1. So it makes sense that this will be 128. It's a little bit of a decimal there. And then we multiply that by the heat of sublimation. Again, sublimation means a change in state directly going from a solid to a gas. So it completely skips the liquid phase, just goes from a solid to a gas. And that comes out to be this many kilojoules, and I just rounded it based on sig figs again. And that's about it.